Just a second. Yeah, okay. Okay, hello everyone. Welcome to this edition of ICTS String Seminar. Today we have the pleasure of having Professor Rob Myers from Perimeter Institute of Theoretical Physics, and he's going to tell us about quantum extremal island made easy. So over to you, Rob.
Okay, well, thank you very much. It's a pleasure to be here today. The first thing I wanted to say, well, the title of my talk, but I've been working with various collaborations of smart people, in particular Vincent Chen, a PhD student here, Dominic Nunenfeld, a postdoc at Perimeter, Ignacio Reyes, a postdoc at AEI, Josh Sandor, now a PhD student at Stanford, and Juan Hernandez and Shanming Rand, both my PhD students here at Perimeter. In any event, let's get started. So here, if anybody's seen me give a talk in the past 10 years, you know that this is my favorite slide to start a talk with about holographic entanglement entropy and the intriguing geometric realization or calculation of entanglement entropies in the boundary conformal field theory in a holographic setting. And this has really been a very fruitful forum for discussion between the bulk and the boundary. In holography, we've learned new things about quantum field theories, but it's also allowed us to learn new things about quantum gravity. And what we're learning about now in the past year or so is we've been getting new insights into the black hole information paradox. And so just very briefly, I'm illustrating it here with this Penrose diagram, which is in flat space. We begin initially in a nearly flat space with a pure state. The matter degrees of freedom there can be excited and come together and collapse, forming a black hole. As Hawking taught us, that black hole slowly leaks radiation that looks thermal and emerges here near Scry plus, and it's carrying away the energy, and so the black hole begins to shrink and eventually disappears, leaving us just with the Hawking radiation at late times. But according to Hawking's calculations, this looks like thermal radiation. And so what we've done is we've gone from a pure state to a mixed state, which is in contradiction with the basic tenets of quantum theory. So I started by talking about holographic entanglement entropy. So how can we phrase this tension in terms of an entropy? Well, it's very easy. Essentially, we can draw a plot here of the entropy carried by the Hawking radiation as a function of time. Initially, there is no radiation, and so we begin down here at 0, but then as the black hole evaporates, we gain more and more radiation and more entropy, and so it simply grows until the point where the evaporation process ends, and then we're just left with this cloud of Hawking radiation with a constant amount of entropy. Now, Page, though, Don Page looked at this a number of years ago, and he just argued on very basic principles that if we want to think of the black hole, or we want to think of this system as a proper quantum mechanical system, then the entropy here in the Hawking radiation has to be bounded by the entropy of the system it's entangled with, namely the black hole. And so at some point in the process, when the black hole is becoming smaller and smaller, it actually provides a bound, and so the entropy in the radiation must start decreasing, and if it's a unitary process, it must end up back here at 0. And in that process, then we're seeing not just a rise, but also a slow decrease, and this is hinting that there must be additional correlations between the Hawking quanta that are emitted at early and late times, and that's what would be causing this decrease in the radiation. And so just in the past year or so, using insights from holographic entanglement entropy, we've really been able to compute that page curve in a controlled way. And it was really a program that was kicked off by these first two papers in the spring of 2019 by Pennington, and then a second one by Almeri, Engelhardt, Marolf, and Maxfield. And I'll also be relying very heavily on the insights of this third paper, which came out last August. And since then, there have been a whole raft of papers, and this author list is no doubt incomplete, but there are many people who have contributed to the area by this time. But I want to return back to this third paper, and they summarize the result with the following prescription. They came up with what they call the island rule. And so generally, one of the insights in these papers is that, you know, if I'm doing holography, typically we have reflecting boundary conditions, and so the black hole does not evolve. Well, it may be excited, and it may some excitations may fall in, and we rapidly get to a final state. But certainly the black hole won't evaporate in the way that I described on the previous transparency. And so what they do is they usually speak about a system where I have not just the black hole, but an auxiliary reservoir, which is non-gravitational. Typically we call that the bath, which captures the Hawking radiation. And then I can manipulate the Hawking radiation there or calculate with it in standard quantum field theory ways. But their prescription for the entropy of the Hawking radiation was given by this formula here. And so not only am I taking into account the entanglement entropy of the quantum fields, the Hawking radiation that's been collected in the bath, but I also combine that with potential space-like regions in the gravitating region, in the black hole region. And these are the so-called islands. And I'm supposed to consider all possible regions like that. And I extremize this quantity where I have the entanglement entropy of the Hawking quanta in the reservoir in as well union with the islands. But then there's also a gravitational contribution coming from the boundary of the islands. And so this is just the usual Bekenstein-Hawking entropy. And so in the, returning to the case of the evaporating black hole, in the early stages, one can examine this, and the natural island or the extremal case is just given by the empty set. There is no island. And so all we're really doing is evaluating the entanglement entropy of the quanta in the bath. And this is essentially Hawking's calculation. And so what we see in the early stages is this rise that was expected in the entropy of the radiation. But then at later stages in the evolution, or at a very late stage, as the evaporation process proceeds, we build up a lot of entanglement between the quanta in the bath, the Hawking radiation, and the quanta behind the horizon. And so then we find a new saddle point, or a new extremum of this formula, where there is a non-trivial island or a region in the black hole geometry, which reduces the overall entropy and in fact produces a result like this, where now the entropy is decreasing as the black hole continues to evaporate. Now, I'm not going to go into those calculations in any great detail. In fact, most of my talk is going to be about pictures and very few calculations. There will be equations, of course. But I just wanted to highlight two key ingredients in these early calculations. One is that they used very simple models, in particular two-dimensional form of gravity called JT gravity. And there's an idea of quantum extremal surfaces. So I wanted to touch on those very quickly before we proceed with an example. So if I think about 2 dimensions, then the usual Einstein-Hilbert term is just a topological invariant. And so that doesn't provide us with a useful action. So they're working with a model developed by Jacqui and Teitelbaum, where one introduces an extra scalar field here in front of the scalar curvature. And that provides us then with a dynamical theory of gravity. And this kind of an action can be described or can be derived by thinking about the near horizon physics of extremal black holes in higher dimensions, but it also emerged in a holographic setting in the context of the so-called SYK model or Sachdev-Yi-Kataev model, where one has a quantum mechanical system of a number of fermions and random couplings connecting those fermions, and one averages over an ensemble of couplings. And the holographic dual, well, it was really, I think, Kataev that argued that this was equivalent to some version of the Jacqui-Teitelbaum gravity. One thing that's going to be important is we're not just thinking about this gravity, but we're actually going to be coupling it to a CFT. And so we should just keep that in mind, that whenever I'm talking about JT gravity, I really mean this theory of gravity coupled to a conformal field theory as well. Now, in the context of this theory of gravity, we talk about black holes. But if we look at the equation of motion here for the scalar field for the dilaton, we see that R, the Ricci scalar, is being set to a constant. In fact, that means that the entire Riemann tensor is covariantly constant. And with a negative cosmological constant, then locally the geometry is just ADS2. So when we say that there's a black hole, in fact, what we're doing is we're looking at two-dimensional anti-de Sitter space, but we're putting a set of coordinates on it where there's a particular, if you like, observer horizon. What really makes this special, though, is the profile of the dilaton, and that, well, behaves in a particular way in this background, and it's really the dilaton that in some sense gives meaning to the position of the horizon in this two-dimensional space. Now, we wanted to talk about entanglement entropy, or in this case, holographic entanglement entropy. The boundary theory is just a quantum mechanical system, but in the context of a black hole, we can think we have two such systems in a thermal field double state, and so there's entanglement between those two. And so a region would be, say, a time slice over here on the right boundary, and I can ask, what's the entanglement entropy with the remaining degrees of freedom or the other SYK system on the other side of the black hole, or represented by the boundary on the other side of the black hole. The usual Ryu-Takinagi prescription would, well, I'm supposed to extremize A over 4G. Essentially what I'm doing is I'm extremizing what's ever in front of the Ricci scalar or the Einstein term. And so in this theory, what we're doing is we're actually extremizing the dilaton profile. And so if I look for the extremal surface, it'll be, as expected, this point that sits on the bifurcation surface of our two horizons. Now, I said, though, that in these calculations, the one that led to the page curve, we have to think about extending that prescription to quantum extremal surfaces. And so in that case, what we're doing is we're not just extremizing this geometric formula that appears in the standard RT prescription, but we're also taking into account the quantum entanglement entropy of the matter fields in this space-time. Remember that I said there was a two-dimensional conformal field theory that's wandering around or interacting with the gravity theory. And so in this case, what I would need is a Cauchy slice or a partial Cauchy slice extending from my quantum extremal surface out to my boundary region. I would do a standard QFT calculation of the entanglement entropy there. I'd add that to the geometric factor. and that's the quantity I'd extremize. And that's a prescription that was developed by these folks here on extending the usual RT prescription to include 1/n or quantum corrections in the bulk. One of the comments I can make here is I've drawn two different Cauchy slices. In fact, I'll get the same entanglement entropy because of unitarity on those two Cauchy slices. So that won't make a difference in this extremization, the precise choice of that Cauchy slice. I really have to move this dot around, or I have to move the extremal surface around to see a change in this quantity. And so it's really finding the position here that tells us, well, that the font gives us this extremum of this particular problem. Okay, so those are the two ingredients that went into calculations, at least in the early papers. And so I'd like to talk about an example, but I'm not going to actually talk about the case of the evaporating black hole that I sold you on with that graph, but instead I'm going to think about an easier system to calculate with, and that's a black hole in thermal equilibrium. So we have this simple JT model of gravity and its holographic equivalent, which are these quantum mechanical systems. And there, what I'm going to do is I'm going to prepare a state with a 2D black hole in thermal equilibrium. And that's really just the Hartle-Hawking state. And so we know that that's associated with this Euclidean black hole geometry. The place where we had a horizon becomes a fixed point of a rotational symmetry here that's given by the Euclidean time direction. I want to have that state be in equilibrium with our bath. We want to connect it to a non-gravitating system. And so I'll represent that in this picture to get a bath, which will for us contain, again, the two-dimensional CFT. I'm just thinking about a path integral on a thermal cylinder. This thermal cylinder actually has infinite extent in one direction, so it's on a half line. And the radius of circumference here in my picture is the same as the radius of circumference of the asymptotic black hole. And that's just indicating that these two systems have the same temperature. And so they are going to be in thermal equilibrium. Now, one can, well, I drew a Euclidean instanton or a Euclidean solution. I said that I wanted to prepare a state. And so a way to think about that state is I can cut my solution in half by, that's what this dotted line is indicating. And then I can take away half of it, and I can think of the Hartle-Hawking state as the state prepared on that dotted line. So in the next slide, I'm taking that picture, I'm squashing it out flat on the screen. Here's my state that I've prepared. And then I can evolve it forward using normal Lorentzian time evolution. In the bath regions, that was non-gravitating, that was just flat space. And so it evolves forward. And what I get is this wing here, or this flat geometry, albeit there is a thermal bath of quantum field theory degrees of freedom wandering around in here. In the gravitational region, I evolve forward, I get my ADS2 along with the appropriate dilaton field. And so this is my JT black hole. And again, there is a thermal bath of conformal field theory degrees of freedom. I can think about evolving that forward or backwards in time. And so I might throw away the Euclidean and I just have my Lorentzian solution that looks like this. But again, we prepared this special state on this time slice here that runs through the middle. Now, this is a thermal equilibrium. And so one might ask, well, why is there an information paradox in this particular setting? Everything's in equilibrium, nothing's changing. But in fact, if we think about it at the microscopic level, the black hole and the bath are continuously exchanging radiation or exchanging quanta. And so, for example, we might have two correlated quanta in our initial state both in the bath regions. In this case, that quanta wanders off in the flat space or in the direction of the bath, and so it just remains a part of the bath radiation. In this case, that quanta wanders into the gravitational region and then eventually falls behind the horizon of the black hole. And so that would be a process in which the entropy of the bath is increasing. Similarly, you can think about quanta that start their existence in the gravitational region. Again, one falls into the black hole, the other climbs out of the gravitational region and into the bath. And so again, that's a process that's increasing the entanglement between the gravitational region here and the two bath regions on either side. So what does a page curve look like in this particular situation? Well, initially at any event, or the naive picture would be just this curve here, that as that state evolves in time, and I'm exchanging more and more quanta, the entropy just increases. And it continues to increase forever. Remember, I had a half line's worth of CFT degrees of freedom, i.e. there's an infinite bath connected on either side. And so this process can continue forever. And in principle, this entropy could continue forever. But if I think of the black hole as a quantum mechanical system that can only store a finite amount of information, then in fact the curve should cap off at a certain point, and I should start recycling, or the black hole should start recycling the quanta that it's absorbed and start emitting them out into the bath region again. And at that point, when that kicks in, then the entanglement entropy should simply be fixed at some constant. And in fact, one can use this particular model that I talk about. I can apply the island rule. And indeed, this is what I find. At early times, if I'm looking at the entanglement entropy of the radiation in the bath, so on these blue slices here, at early times, there's no island, or the island is simply the empty set. This is a standard quantum field theory calculation, and as expected, the radiation grows. However, at late times, one finds a new saddle. One finds that by including quantum extremal surfaces or an island in the black hole region, that in fact the entropy is reduced. And in this setting, in fact, one finds that the entropy becomes a constant. And so this region is then our example of an island, or a quantum extremal island. And it's argued, or it was argued, that there's information about the black hole interior then that's being encoded in the bath radiation. And also a surprise at the time was that in this particular case, the quantum extremal surfaces actually extended outside of the horizon. And so that the island actually not just included the inside, but a little bit of the outside of the black hole. So that's an example of a calculation. It's an example that I'm going to emulate later on in the talk. But in the early days, at least, these calculations perhaps raised as many questions as they answered. People asked, how important was it that I was working with 2 dimensions, or in particular this SY, or this JT gravity with the SYK dual. But basically the message I have today is I would like to provide a model where we can see that the insights about the page curve that we're learning here are really, we can understand them in terms of properties of more conventional, or that we've learned in the context of holographic entanglement entropy. And so I'm trying to put it in a more conventional context. And I've been talking a lot, and so I feel like I should pause and just ask if there are any questions about this introductory material.
Perhaps a
Well,
question. Oh, sorry.
there is a question. Marco, yes.
Yeah. How important are the, well, actually, it's a double question, maybe, since nobody else is asking. So first question is, how important are the boundary conditions when you glue the CFT to the gravitational region in this two-dimensional example? In particular, I seem to remember that in one of these papers, at least, the boundary conditions are set to conformal, and for the bath. And is it important that instead the JT gravity has natural boundary conditions which are only near conformal? And the second question is if there's some basic misunderstanding that I have about the island formula, so I'm just going to ask. In the same entanglement entropy, I think you can get directly on the CFT side, just by a CFT computation, and seeing that the two twist operators that you had as points in the bath obey different OPE limits. So in the late time, they would be dominated by the identity in the defect channel. And this seems to be completely independent from islands on the inside. That computation would be the computation that you would do in a non-holographic CFT, in a CFT with a boundary to compute entanglement entropy. So why is that computation giving the correct result? Even if we never talk about islands, we compute just entanglement as if it was just the entanglement of QFT degrees of freedom.
So the boundary conditions, I mean, I'll say that, we are changing the boundary conditions from the conventional holographic boundary conditions, and we're letting the CFT degrees of freedom leak out of our gravitational region. And that, again, I'll just emphasize, was an important part. You want to zero in, though, on the details of that. And you can add that to the list of questions here. How important were the boundary conditions? What I'll present you with is a holographic model where, again, actually, I would go to you and ask you more about the details of the boundary conditions. I don't think that it's extremely important, but it is important that the low energy degrees of freedom are being allowed to leak out. I mean, usually they're simply talked about as being transparent boundary conditions, but I don't really know. The truth is, I don't really know what's hidden in that set of words, at least to a degree of rigor that would make you happy. The other question, I'm not exactly sure the question that you're asking. There's a set of slides that are or advocate a purely quantum field theory degree calculation that should have shown us, or will show us, a page curve without even talking about gravity. But sadly, they're in the extra slides part of the talk. But maybe you can ask me about it again at the very end. Okay, so basically what I would like to do is I'd like to answer that first question in the negative and say that, two dimensions wasn't important at all. And I'm going to do that by setting up a framework, a holographic framework, where we can talk about essentially the problem that the island calculation that I talked about before in any number of dimensions. And so to get started there, I have to take us back about 20 years, and I want to remind us about Randall-Sundrum gravity. And there's a footnote, or I guess not a footnote, there's a note here at the top of the slide that Andreas, who I think is out in the audience, wrote a paper about similar ideas last spring. But the point is here, all I've got is my standard Einstein gravity in the bulk coupled to a negative cosmological constant. But the new thing that we're going to do is we're going to stick a brane in there, and it's going to be a brane with tension, and that brane will back react on the system or on the gravity, and I'll get to the details of the resulting geometry, but I'll just say that one of the fascinating aspects of this is that one finds a new mode of the graviton that's localized in the vicinity of the brain. And that gives rise to an effective theory of gravity. This is a side comment that actually, motivated by the two-dimensional models, one can also think about adding intrinsic gravity terms on the brain, but that's not going to be important for anything that I do today, but you can go look at the papers if you want more details about that. So I'll just skip that part. We'll just work with this. We'll look at one can look at the details of that localized graviton mode, and one finds that one can build an effective action for gravity on the brain. And, there's an effective Newton's constant here, which is a combination of the ADS scale in the bulk and the bulk Newton's constant. There's an effective cosmological constant term here, and that scale is set by the back reaction. You can see the back reaction in this formula where I have the bulk Newton's constant and the tension of our brain. And one comment is that we are going to do a tuning in our theory such that this scale is very large, or the cosmological constant on the brain is very small. And so we want this factor to be small. And that means that this is much smaller than the bulk curvature scale or cosmological constant. And what that buys us is that in our action, we see the cosmological constant term, a Newton's constant, or a Einstein-Hilbert term, but then there's a whole series of higher curvature terms. But in this regime here, these terms will contribute in a way that's suppressed by powers of the bulk ADS scale over the boundary ADS scale. And so essentially in this regime, we can think that what we're working with is just Einstein gravity coupled to a cosmological constant. I promised to talk a little bit about the geometry that we have. Well, we can calculate the position of the brain using the standard Israel junction conditions. And so the first thing we have here in this cartoon is just a cross-section of global ADS. That's the time slice. I'm going to foliate ADS by these, so I'm ADS D plus 1. I'm going to foliate it by anti-de Sitter slices in D dimensions with this metric here. And then I'm going to cut off the geometry at a particular position, rho brain, which will be near the asymptotic boundary over here. Well, that will turn out what this tuning corresponds to. What we do then is we take two copies of that cut off geometry and glue them together along the cutting surface. And that is really then the position of the brain, this green line. And it's the jump in the extrinsic curvature being related to the tension of the brain that then defines the position of the brain. And that, well, these formulas here are the standard Israel junction condition. As an aside, I can also say that given that effective action, you can also simply solve the brain equations of motion. And there you'll get that the curvature scale here, LB, is, well, there's some formula relating the cosmological constant to all of these various higher curvature, well, the Einstein term and the higher curvature terms. And you get some formula for the curvature scale, and then you can scan through this foliation and you can find the surface where the brain has to be positioned. And so that's just showing that there's a consistency between this effective brain action and this bulk description in terms of, well, the standard Israel junction conditions. A warning is that I'm going to be lazy, and rather than drawing pictures like this, I'm typically going to be drawing pictures like this, where I just have a circle and a line representing the brain running through the middle. But then the warning is that, well, will not appear, but one should keep in mind that there's a lot of extra geometry hiding in the picture here in the vicinity of the brain. And so this is a cartoon of a cartoon. And so that's just a warning. A comment is that in this system, you know, sometimes we'll be thinking about holographic entanglement entropy, and sometimes the RT surface crosses the brane, and you find a contribution there that is proportional to the Bekenstein-Hawking formula for this particular effective action. And I'll comment more on that towards the end. But what we have now is a holographic system with not just two, but rather three possible descriptions. If I think about the boundary perspective, what I have is some d-dimensional holographic CFT, and it's coupled to a conformal defect. And that defect is the position where the brane reaches asymptotic infinity. Of course, the usual dual, I just go to the bulk, and it's that description that I talked about before. I've got Einstein gravity coupled to this brane, which back reacts on the system. Now, what Randall and Sundram do, though, is they give us another perspective of this defect physics or this brane physics. And I can think that I've got my boundary CFT, but instead of being coupled to a defect, it's coupled to a region that has an effective theory of gravity. The geometry there is ADS-D. And in fact, in this gravitational region, we also have another effective copy of the CFT, or in fact, in my construction, there are two boundary CFTs that are weakly coupled in this gravitational region. That's an effective description, and in fact, one of the things that Randall and Sundram stressed is that there's a cutoff that comes in that theory. But at least if I'm talking about low energy excitations, I can work with that gravity theory that we had on the previous transparency. Now I want to take this particular setup, and I now want to think about the black holes in thermal equilibrium, the problem that we studied, or I briefly ran through in 2 dimensions, but now I want to raise that problem to d dimensions. But for the moment, what I'm going to do is I'm going to set aside the brane, and I'm just going to think about empty ADS space. And I'm going to remind you that that space can be described in terms of a hyperbolic black hole geometry. So what I'm doing is I'm taking empty ADS and I'm putting this coordinate system on it. And so we can see that GTT has a 0 at some particular position of the radial coordinate, and correspondingly, you know, the rho component is blowing up there. One of the features, though, is it's a hyperbolic black hole, and so the spatial geometry here is in fact a hyperbolic, or a hyperbolic plane in d-1 dimensions. And so what that's describing then, in this particular perspective or this particular conformal frame, is I've taken the boundary CFT, I've put it on my hyperbolic plane, and then there's time as well to fill out the extra dimension, and I've put it in a thermofield double state, and so it's 2 copies of this entangled at a very special temperature, and that temperature is related to the radius of curvature of my hyperbolic plane. So the temperature is 1 over 2 pi r. So that's, and that's something we often also call ADS Rindler coordinate. So it's really just looking at empty ADS space, but I've put a coordinate system on it where these observer horizons appear. But it also has an interesting description in terms of a thermofield double, in terms of the boundary as well. Now I want to talk about the system with the brane, and so all I'm going to do is I'm going to take that geometry and I'm going to stick the brane in the middle. I'm going to literally cut through the middle of the space in that coordinate system, but now introduce the brane. And then what I've done is I've enhanced the system by sticking in a conformal defect in the boundary theory. And so my thermofield double state describes not just the boundary CFT, but the boundary CFT coupled to a conformal defect on this particular geometry, at this particular temperature. Now remember that what I had in 2 dimensions was a gravitating region that was ADS2 with special coordinates that made it look like a black hole. Then I had these boundary wings or non-gravitating regions, which in this case was sort of half of Minkowski space. What I've done in this setup is I've sort of enhanced it to D dimensions. I have a hyperbolic black hole here, which is really just anti-de Sitter space with a special coordinate system to introduce a horizon. In the bath regions or the non-gravitating regions, rather than having flat space now, I have a hyperbolic geometry cross time. And what the picture here is indicating is that rather than being at the end of the space, the defect is really in the interior or sitting in the middle of this bath geometry on either side.
Sorry, I have a question. Is
Sure.
it right that now in this hyperbolic setup, you've lost the IR cutoff on the spectrum? So if you just look at the boundary theory, is it correct that the spectrum is continuous in the thermofield double state you mentioned?
Yes. I've gone to a conformal plane. Yeah, I mean, originally I was drawing pictures where we were sitting on a sphere, but I've gone to a conformal frame where I've taken this singular transformation to sort of blow. Well, I'll draw a picture in a moment, but yeah, I've done a singular conformal transformation, so I have this infinite space here.
Okay. Okay.
Yeah. Okay. So this is a picture of one side. This is one of the baths. Again, the geometry is this hyperbolic plane cross time. The Penrose diagram just looks like the Penrose diagram for flat space. The conformal defect is a hyperbolic slice sitting in the middle of the space. And so that's the green line here. If I think about where that sits in my ADS space, it's really this diamond between the two, well, either one of the two horizons. So there, I've done in this singular conformal transformation so that spatial slice becomes the hyperbolic geometry. And also I'm picking out a finite time interval here. And there's another copy of that on the other side, or the thermofield double. If I think about what kind of entanglement entropy calculation I want to do, well, I want to look at the quanta in the bath and in the copy of the bath, the thermofield double. And so I'll take some large region that extends out to infinity, and I'll just to regulate the problem, I'll keep it a short distance away from the defect that sits in the middle of the space. If I ask how things evolve as I go forward in time, well, the endpoints, well, are drawn up along this line, which is a constant proper distance away from the defect, but they're all drawn up in the usual way to a common point here at the top of the diamond, which is time like infinity. And that's happening on both sides of the defect and on both sides of the thermofield double or the double state. And so if I look at it, if I'm taking a cross section of the space here, then here's my brain running through the middle. The horizon, this line here, would run orthogonally to that. Again, remember there's a lot of extra geometry hidden in there. I've taken a line from some point near the defect. It runs out to infinity. But at that point, it's actually meeting the other, the other region of the thermofield double copy. And so there's a region over here, or I'm looking at the entanglement entropy of a region here on this side of the geometry and a corresponding one on this side of the geometry. And I can ask, well, how does that picture evolve in time? As I've shown in the top right there. And well, what's happening is those endpoints are moving closer and closer to the defect or to the brain. And so our blue region is stretching out. Now that may be a picture that's reminiscent from various calculations people have thought about in holographic entanglement entropy. And so we'll take a side note here. Again, we've taken away the brain. We're just thinking about empty ADS space. And we've got two regions, two disconnected regions on either side of the ADS boundary. And depending on what regime we're in, we may either find that the Ryu-Takenagi surfaces take this form or they take this form. So a disconnected phase and a connected phase. And it really depends on the size of our two regions compared to the size of the boundary. But there are these two competing saddles. But I've also shaded in the entanglement wedge here, because one of the lessons learned from this story is that of entanglement wedge reconstruction, which says that I can use boundary data to reconstruct what's happening inside the entanglement wedge. In this phase, the disconnected phase, that's not too surprising that the data here tells me about can tell me about what's going on in this region near the boundary, and similarly on the other side. But of course, in the connected phase, the surprise is that we know what's going, or we can use the data on the two boundaries to tell us about what's going on in the middle of our anti-de Sitter space. Now, again, all I'm going to do is take this and then overlay it with the pictures that I had before. In particular, I draw a green line down the middle, which says that there's now a brain sitting in the middle of this picture. And the idea is, again, that one finds that there's a phase transition between a connected phase and a disconnected phase. In particular, this connected or disconnected phase is what I see at early times in the evolution of my thermofield double state. So the RT surfaces in this context are actually joining opposite sides of the black hole. And as we evolve in time, the entanglement entropy grows. The entanglement wedge, as I said before, only tells me about these regions that are near the boundary of the ADS space. And this, of course, is the growth phase on that page curve that I showed you before. However, at late times, we go over to this connected phase. The details of that transition are going to depend on the presence of the brain and the back reaction. But in this case, the RT surfaces actually join points on one side of the horizon or one side of the black hole or the other. And it turns out that the time evolution here, that the entanglement entropy is naturally fixed. And in this case, however, again, I've shaded in the entanglement wedge. And again, data on the boundaries here can tell me what's happening in the middle of the space, but in particular on the brain. And that region, that intersection region on the brain is none other than, from the gravitational perspective, this is the quantum extremal island that we were talking about at the beginning of the talk. Oh dear. And so this is the page phase. It's also useful to think about this entanglement entropy problem, not in terms of the blue regions, but in terms of the complementary regions, these two black regions. In that case, you can compare this calculation to calculations done by Hartman and Maldacena. And this evolution where initially the entanglement entropy grows and then at late times is constant is just in there. From this perspective, the system is thermalizing, and it does so very rapidly, but then it reaches this stationary state where the entanglement entropy no longer grows. There's also this question that, in fact, these two intersection points are outside of the horizon. Remember, I noted that was a surprise before. Here in this discussion, it can be described entirely in terms of entanglement wedge nesting. This black region is only a portion of the black hole boundary, and so this entanglement or RT surface has to lie inside of the asymptotic region to one side of the black hole. And so this was our two-dimensional model, but in fact, we've reproduced it now in D dimensions with an induced Einstein gravity theory on the brain. And so these are just some graphs from one of the papers showing this page curve in various dimensions, d equals 3, 4, and 5. There were lots of questions. Clearly, 2 dimensions isn't important. JT gravity isn't important. The ensemble average of the SYK is not important. Another question one might ask about is this tension. If I think about this island formula, I have the bath radiation, and in fact, there's an entanglement entropy here involving the bath and an entanglement entropy here involving the bath. And if you look at this paper where they introduce this idea, they distinguish between the 2 sides of the equation. They say, here I have a full quantum description, here I have a semi-classical description. And so you might ask, what's up with that? Well, remember, I had these 3 descriptions of our holographic system. Most of my calculations were done in the bulk, and those can be related to the bottom description, the bulk description, or they can also be discussed in the context of the boundary conformal field theory. These descriptions, I would say, at least in quotes, give a full quantum description of the radiation. They, in principle, give us a full UV complete description of what's going on. In contrast, I said that this description using Randall-Sundrum gravity is really an effective description of the system. In particular, there's a cutoff in the copies of the boundary CFT living here on the brain. And I also, well, there are other features that we've thrown away when we go to this description. And so it's clear that this description is not a complete description of the physics. And so this is what they would describe as a semi-classical description of the radiation and Hawking partners. I'm going to move on to another question, and I see time running, but I will pause for a moment just to ask if there are any questions about this holographic setup and the page curve for the black hole or the thermal equilibrium.
Yeah, I have a question about this last point that you made about what one means by SQFT. I thought the way we should have understood this SQFT was in the sense of some, Faulkner-Leukowitz-Maldacena kind of thing, where you basically just consider free fields in the region, and that's some core-strained entropy. But here in the last slide that you have here, you seem to be saying something slightly different. You seem to be saying that, there's some effective field theory, and within this effective field theory, you do this computation, but that seems like it's more fine-grained than what one would usually understand by SQFT in this Faulkner-Leukowitz-Maldacena kind of formalism. I mean, usually I think we don't worry about.
I guess I haven't emphasized it here. I don't know if this is going to answer the question. I'm going to throw out an answer, and then I'm going to go on, because I'm going to talk a lot more about the entanglement entropy, and then I'll ask you to indulge me and try and ask the question again at the end if you're unhappy. It's just that I know I'm going to run out of time. But what I'm going to say is that, in what they were doing, Leukowitz, in the initial discussion, what they were talking about was, I have this geometric contribution, and then I have 1 over n, or quantum contributions in the bulk. One of the things that I haven't emphasized is that is the calculation that would be happening here. In this effective, or this brain perspective, in the gravitational region, you're using holographic entanglement entropy. Again, for the Ryu-Takenagi formula, that's just A over 4G. And then you're including quantum corrections of the CFT on the brain, and in the bath. But in our calculation, in our bulk calculation, all of that got translated to a geometric formula. And so, a natural question you might ask is, well, how did I get from that geometric formula, that Ryu-Takenagi entropy, to this island rule, which has a very different form? And I think that's at the heart of what you're asking, and that's what the next few slides are going to talk about. My perspective was not to answer Suvrat's question. My perspective was that this is actually a warm-up for holographic complexity because my invitation said we're interested in holographic complexity, and so I wanted to say a few words about that. But let's warm up with this question here. Is that okay, Suvrat? I'm sorry.
Yeah, that's sure. Actually, you can also go on for some time. We're not that strict about time, so yeah.
Okay.
Yeah,
Well,
sure.
let me do this, and we'll see. So I'm starting with this Ru-Takinagi prescription. I'm imagining here that we're in the connected phase. I have two regions, on either side of the ADS. I'm not necessarily worrying about the black holes and the thermal equilibrium. I'm just saying that I've got my brain in the middle of the geometry, and I've chosen a boundary region that has a left and a right component on either side of that brain, or on either side of the conformal defect in the boundary theory. How do I go about solving for the Ru-Takinagi entropy, which is really this area in the bulk? And if I had an intrinsic Einstein term on the brain, we also showed that you'd get a contribution on the brain, but you can ignore that little bit. And we're just going to try and extremize the area in the bulk. And if you do that, you're just solving a local equation. And it turns out you're not going to get one surface, but you're going to get a whole family of surfaces in the bulk. And the difference between them is where they are going to end on the brain here. Given the data that I've given you, I can solve this equation, and it won't specify the boundary conditions here. The boundary condition on how the surface intersects with the brain is a separate part of the problem. But let's look at these surfaces with different profiles on the brain. Again, this would be the boundary of my so-called island. Well, there's going to be a contribution here coming when the surfaces approach the asymptotic ADS boundary. Those have a geometric interpretation, they're UV divergent, and so I'll find the usual area law term, and then if I'm in sufficiently high dimensions, I find terms that involve integrals of geometric quantities over the entangling surface that defines the boundary of my region R. There's of course finite contributions in the coming from the middle of the ADS geometry here. But then what I want to highlight is that in the regime we were talking about, this brain is being pushed out towards what looks like an asymptotic region of the ADS geometry. And so there are terms that would be the counterpart of these UV divergent terms, but because of the presence of the brain, those terms are now finite, and they can all be interpreted in terms of the boundary theory. And in fact, it turns out, if you calculate carefully, that what those contributions turn out to be are they're giving you the Wald-Dong entropy of this surface, sigma r, in the brain theory. And so we began with the usual Bekenstein-Hawking term that was associated with the Einstein-Hilbert term in the boundary. But then if you're careful, you can also pick up extra terms involving curvatures, or in fact, extrinsic curvatures that come or are related to the higher curvature terms. I didn't give you the specifics of those terms, but you can find them in the paper. Here I'm giving you the specifics of the contributions to the entropy, and you see that those match by the usual prescription given by Wald and the correction term that Dong introduced. But we haven't completed our extremization at this point because, as I said, I have a whole list of different potential RT surfaces, but we can simply find that the appropriate or the true extremal surface. Well, there's a comment here about the UV divergent terms all being identical, but we can find the true RT surface by simply varying now, doing a second step in our extremization by varying that profile on the brain and simply finding which amongst all of these potential surfaces, which one yields the minimum area. And so I can now interpret the various contributions. You know, again, I said that there's this geometric term associated with the gravity theory on the brain. These two contributions I can think of as the quantum field theory entropy associated with the boundary CFT that's living on the asymptotic boundary, but also here on the brain. And so what we see is that these two steps in evaluating the RT entropy are, in the first step, extremizing away from the brain. What you're doing is you're evaluating this quantity here. You're evaluating the gravitational entropy of the island boundary on the brain, and then you're evaluating the QFT entropy of the CFT degrees of freedom in the bath and in the island. And then this extremization here is just the extremization that gives you the final, it picks out the correct surface by varying the profile of the island boundary on the brain. The one thing was that here in this formula, we've got the Bekenstein-Hawking entropy, but in fact, what we saw is that the brain theory is actually a higher curvature theory, and holography just spits out for us the natural geometric entropy or gravitational entropy there, which is the Wald-Dong entropy that appears there. So that's an interesting way to understand how we got from this geometric formula from the bulk perspective to this island rule in the brain perspective. As I said, for me, though, this is just a warm-up for holographic complexity. And so we can ask a similar question. You know, there's a prescription in holographic complexity that says complexity is equal to volume of particular slices or codimension one, extremizing codimension one surfaces that run through the bulk. I'm actually using, or I'm going to be thinking about a version of this called subregion complexity, where I'm actually going to use part of the asymptotic boundary, and then this surface in the bulk runs between that boundary surface and the RT surface in the bulk. So that's not a complete Cauchy surface of the entire ADS space, but just of this, of the entanglement wedge here. In the case of brains, we don't have a clear argument that says that, or a derivation that says you should include a similar geometric term if there is an Einstein term, say, on the brain. And well, we make some, we allude or we show a certain sense of consistency there, but you can just ignore this term again. The real question is, okay, this is our bulk perspective. This is something that we're used to working with, but what's the corresponding island rule, or what do I see from the perspective of my effective gravity theory on the brain? And again, well, the approach that we're going to do is we're simply going to take the same analysis that we did before, which involved the Pfefferman-Graham expansion near the boundary, and we're going to see what the various contributions in this geometric formula translate to in terms of our brain theory. And then this was well, there's just a comment here. I'm taking a partial Cauchy slice. I'm using the subregion version of the argument just to make, well, it becomes more interesting. So in this case, what I'm doing in my usual complexity equals volume prescription is I'm extremizing codimension one bulk surfaces. And the first step will be to do that away from the brain. Again, that's a local equation in the bulk. Here's my cartoon, again, of the two ADS regions on either side of the brain. The colors have changed slightly. My region has these two components on either side of the conformal defect. My boundary, or the bulk surface that I'm interested in, is bounded by that asymptotic region and the entanglement, or the Rutaki-Nagi surface here in the bulk, the sigma r. And I'm also going to denote the profile of the intersection of my bulk surface with the brain. That's really an island by sticking this tilde there. So I'm trying to extremize this formula. Again, what I'll find is many candidate surfaces. It's hard to draw because they're now coming out of the picture. But 2 points to emphasize. One is that this, I'm assuming the entanglement entropy calculation has been done. And so these boundaries here are fixed, the sigma r and the little sigma r. And the other thing is, I just want to emphasize that it may not be easy to see, but there really is a degree of freedom, or there's a lot of freedom here. This process of extremizing away from the brain doesn't pick out a single surface, but many surfaces. And if I thought about the problem in terms of the complete ADS space instead of the cutoff region, what you would realize is that, well, the surface in the middle here is going to be defined by the choice of the surface I make, not just on this boundary, but the choice of the surface I make on the other boundary. And so that data is missing in this problem. And so that's the freedom that I have in choosing the profile on the island surface when I solve this local equation. Again, there are many candidate surfaces. I find a set of UV contributions coming from near the asymptotic boundary. I find some finite IR contribution. And then I have a set of terms that were potentially divergent, but in fact, now they give me finite geometric contributions on the brain. And so a question would be, can I relate these contributions to some formula in terms of the gravity action on the brain? And we step back and we think about the Wald-Dong formula. There we had, what Wald, in thinking about stationary black holes, did is he took this variation of the gravitational action, and that was ascribed as the black hole entropy in the context of holographic entanglement entropy, where the surfaces aren't extremal, or they are extremal, they're not horizons, they're not necessarily stationary. There are these extrinsic curvature corrections that, again, can be related in a relatively simple way to the gravitational action. So following a suggestion by these folks here, in fact, you can derive now a geometric or a similar formula for the geometric terms that we found in the brain theory. And so here, this is the effective action of the brain theory. And by looking at various variations, there's a term that gives us what we call a generalized volume, and then there's a term that gives us these extrinsic curvature corrections. And so you can think of these terms here as a geometric complexity that's associated with the brain theory, according to that prescription. Again, we haven't finished doing the extremization. The last step is that we extremize the profile of the island here on the brain. And then what this translates to is the complexity from the brain perspective has this, in the first step, we're evaluating this quantity here, which has a geometric contribution from the brain gravity and a quantum field theory contribution coming from the CFT. And then the last extremization is simply this extremization that picks out amongst the various candidate surfaces. But having gone through this process and discovered this interesting formula, a proposal that we make in our paper is that this actually provides us with a prescription for some generalized version of complexity equals volume for higher curvature gravity theories. And so in that context, I'm not thinking about our brain theory, I'm just thinking about ordinary ADS, but there may be some more complicated theory of gravity in the bulk. And we write down again these formulas as the geometric interpretation, well, the various geometric terms that go into, that should be extremalized to produce the complexity. You might also think that there's a Faulkner-Lukowitz-Maldacena correction, the quantum field theory correction that comes to that. And you've seen that arising in the context, but we don't really have any more to say about that. In fact, there are lots of questions we can ask about this, but I'm going to skip over them. And I'm just going to say that, you know, there have been a lot of interesting new insights, but a lot of interesting questions remain. And so there's a lot to explore. I apologize for running over, but I thank you for your attention. So thank you.
So thank you very much, Rob, for the very nice talk. So maybe we can unmute our microphone and clap up.
Okay.
All right, so now it's time for questions. So if you have any question, please unmute your microphone and carry on.
I would like to ask one question, if I can.
Oh, Roberto.
Hi, Rob. Yeah, nice. Yeah, well, for me, it's good afternoon. Yeah, very nice talk, by the way. I have one question. It's a bit technical. Your black holes all have infinite area, right? Because they are acceleration, they are horizon and acceleration horizon. How do you deal with this? I mean, because otherwise, I mean, if you don't regularize this somehow, what you're doing is infinity equals infinity all the time, right? How does this affect your calculations?
No, we're really taking advantage of that. I mean, in the usual way, like when we work, say when you work with, you know, planar black holes and you're doing hydrodynamics, you talk in terms of an entropy density rather than an entropy. And so I guess implicitly we're introducing a regulated volume in the calculations, but all of the surfaces that we're working with have a, you know, asymmetry in those directions. And so that's just a constant that comes along for a ride.
Is it always a constant, even if you're, because I understand that it can be a constant if you're just considering, say, the black hole horizon, but here you have, isn't there some bulk dependence on this, or is it really a constant that you can always factor out? You're saying that
well, in the problem that we set up, yeah, we actually set it up in a way that it is a constant. I mean, well, this picture is as good as any other. I mean, what we're ensuring is that in this conformal frame, there's a constant proper distance between here and here.
Yes.
And so this is like a belt geometry, but it's actually got it inherits the hyperbolic geometry of the background.
Yes. Okay. Yeah.
And so it really, that hyperbolic symmetry, if you like, is inherited by the problem that we're studying here.
Okay, so what you're doing is that you can impose a regulator that's, or you can take it as a factor that always drops out from the calculations.
Yeah.
Okay. Yeah. But you're not taking a discrete quotient of the hyperboloid or anything, right?
No, we weren't doing anything that formal or that.
Okay.
Yeah, it was just an implicit factor that comes along for the ride.
Okay. Okay. Thank you.
Okay.
Hi, Rob. This is Gautam.
Hello.
Hi. So I have a question regarding the slide that where you talk about the paper of Hartmann and Maldacena. Yeah, right. So are you saying that if one digs deep enough into that paper, then one can actually discover the physics of the island?
You would, well, okay, in the I would say no, because they you know, this became a discussion of islands when we introduced the brain, and that gave us a new perspective on the physics. You know, it really gave us this this third perspective on the physics. And it's really, when I talk about islands, I'm really talking about this perspective where I have a gravitational region here that's coupled to the non-gravitational or the usual asymptotic boundary CFT.
Right.
But apart from that, you know, that all of the words so you wouldn't have seen it in their particular paper, but for this black region, and irrespective of whether there are brains there, I can take all of the words from Hartmann-Maldacena and translate them to our problem. When I'm talking about a conformal field theory coupled to a defect, or just the bulk now with a brain in the middle of it. They wouldn't have had this third perspective, but
because
all of the other words.
Hartmann and Maldacena only talk about the RT surface. I mean, nothing.
That's right.
So you're saying that suppose I insert a brain inside the geometry, and yeah, I mean, it would be very interesting for me because I'm familiar with that paper, and I see. So I have to introduce a brain in the middle of their
Yeah. I mean, again, that's really, in some sense, you know, we use the words in our paper that this is a doubly holographic model. In some sense, what you're doing in this first step in going from A to B is you're doing holography on the defect degrees of freedom. You're producing this gravitational picture. And then you're doing holography on the boundary CFT to fill in the bulk in this picture here. The beauty of that final picture, though, is that all I'm doing are geometric calculations. All I'm doing is the usual RT prescription, but what I tried to describe here or convey here is that that geometric description actually gets translated to something involving, you know, for me, far more involved quantum field theory calculations of entanglement entropies when I think about this brain perspective, where I have a gravitational theory coupled to a CFT.
Very nice.
So yeah, the bulk perspective is really where I'm doing all my calculations, but I'm aware here that it translates to this interesting formula in terms of gravity coupled to a CFT and the new island rule.
Thank you.
Okay.
Any other question to Rob?
Yeah, I would like to keep asking questions about the boundary perspective, and in particular, what are the properties? So if I were to take just a CFT on a thermal circle and compute entanglement entropy, I would find something qualitatively similar for any CFT I consider to this rising and saturating of the page curve, at least the thing that you were mentioning at the beginning.
Yes.
And so what are the features what are the important features introduced by the double holographic setup, and in terms of the spectrum of the CFT, for instance, is if I consider the boundary, which has many degrees of freedom and has a gap in the spectrum, but with a bath which is just free fields, would this work? Would this be qualitatively different? What are the ingredients you need from the boundary point of view to get a specific curve?
Well, okay. I think what you're doing is you're egging me on to show you the extra trick.
Yes, please.
So one of you know, initially, when we were thinking about the page curve and Hawking radiation, you know, we thought here we're going to see unitarity. And so to understand that, we're going to have to understand lots of details about, you know, the underlying microstates and, you know, how the information gets encoded into the Hawking radiation. What are those late time correlations? And the real surprise here is that, you know what, we didn't learn any of that. And instead, what we're dealing with are, again, saddle points. And you know, you know, so somehow we've solved part of the problem. We see a unitary page curve, but we still don't understand in detail the microscopic physics that's going on here. And then I have to skip through this. Oh, no. Okay, sorry. I just have to find my slides. I'm sorry.
So could I say something on that just related while you're finding your slides? Please go ahead.
Sure.
Yeah, I think that what Marco is saying is right, that in a sense, you know, if you just, I mean, I think that's perhaps the best way to understand this, that, you know, you have a defect CFT coupled to a bath, and one would see the page curve in that. And I think what's happening here is that when both of these CFTs, you know, when there is a holographic interpretation of this boundary system, you can use gravitational techniques to do that computation. So I mean, I think it's correct that you could have done this computation by putting everything on the computer, and you would have seen this page curve just on the boundary.
No, I agree with that. You know, 100%. Well, okay. I don't know if it. Well, I can share them for Marco, but you know, the real. Well, okay. What I was going to illustrate here is that what you might have said is, well, why did we expect that we needed to understand all of the microscopic details? And I think for the problem that Marco described, or the generic problem, you would see something like the page curve. Certainly, initially, you get a rise, and finally, you get some kind of saturation. The details of how you get from one to the other would not be as, you know, simple as the curves in the systems that I described. And in those cases, you would have to know all of the details, or you would have to know far more about the details of the microscopics. Or alternatively, as perhaps Subrat was saying, you throw it on a computer and let the computer do the work for you. The real surprise, or one of the surprises that these calculations are showing, is that, you know, it's really it's really all just a saddle point calculation, and it's a competition between different saddles. And maybe I won't bother with the slides, but I mean, I can show them to you later, Marco, if you want, but you can imagine that there are CFT calculations, or certain CFTs, you know, with large numbers of degrees of freedom, where it does become a competition between saddle points, and you do realize the same page curve, which is, I mean, that is the generic behavior of physical systems that you expected, but it's described in terms of a competition between different saddle points.
Okay, so what you're saying, if I understand well, is that the curve gets sharper, right? So the transition gets sharp in
really,
infinite n.
Yeah, that sharp corner is a large n effect.
And yeah, and otherwise it's all the OPs contribute everywhere, but okay, I see.
Yeah.
Okay, thank you.
I'm not. So for a generic state, I think even the sharp corner might just occur, even for finite systems. I mean, it depends on what kind of state you take, but it would be pretty sharp, I think. I mean, if you took a generic state, then you would get, I think, a pretty sharp corner.
Why would it be a sharp corner?
Well, for a generic state, I mean, just because the entanglement entropy would always be the dimension of the smaller part of the system, and so that smaller part just I mean, discontinuously goes from, you know, when you are at half the system. I mean, if you take a big system and divide it into two parts and take a generic pure state in the big system, then the page computation was that the entanglement entropy is generally just the dimension, or log of the dimension of the smaller part of the system. I mean, for some special states, you're right, it may not be sharp, but if you just took some generic state, then I think it would be, okay, you're right, maybe it wouldn't be infinitely sharp. You would have some.
I mean,
yeah, no, I mean, my intuition there is really based on you know, gravitational models again. You know, in particular, if you look at the so-called West Coast paper, you know, who is it, Pennington, Stanford, Schenker, you know, they have some simple two-dimensional gravity theory, but they have a very, well, a more complicated, I mean, it has many steps, transition between one behavior and the other. Again, it's a saddle point, but they just have, you know, many different contributions in going between those, well, the early phase and the saturated phase. And so I don't know, my intuition was that was sort of what I expect or should expect of sort of more generic systems where large N doesn't play a role.
Yeah, I guess. I mean, if you took like a 10 qubit system and you divide it into two parts, the point, you know, the moment you took more than 5 qubits on one side, you would get it. You would get some shit. I mean, entanglement entropy which was going up would start going down. But I mean, you're right that, you know, 5 to 6 is some discrete jump. So unless you're really in the thermodynamic limit, it looks like it's not really totally sharp, because I mean, you have to go from yeah. So you're right, I guess. I mean, it's not infinitely sharp unless you're in some limit. But,
okay, yeah, maybe we're splitting hairs.
Any other questions?
Yeah, may I ask another question about what was already asked about the boundary calculation of the you know, this page transition. So Rob, you mentioned this paper of Ramsdonk and others. So in that paper, you know, one thing I didn't understand is that there's a defect system, which is a 0+1 dimensional system, which is coupled to the 1+1 dimensional system. And the 0+1 dimensional system was just treated as a boundary condition only. You know, the degrees of freedom of that 0+1 dimensional system, there was only one number that was taken from there, that was the boundary entropy. And besides that, you just replace that 0+1 dimensional model itself by a boundary condition for the 1+1 dimensional system. So that I didn't understand, because, you know, when you have a defect like that, like a Kondo model or some such thing, the degrees of freedom of that defect are also important. And it's, yeah.
Okay. So you should ask a question, and then my question was going to be, can you remind me which specific paper are we talking about?
I think the first paper of
okay, yeah.
Ramsdonk et al. I forget.
Yeah, no, okay, I know which paper we're talking about now. And then what's the question?
In that one, so, you know, you have let us say I had the SYK, which is some quantum mechanical system coupled to a bath which is on a half line, and the SYK is at the end of that line. And so they don't talk about details of SYK or anything. They say that, well, there is a defect system, and that leads to a boundary condition for that bath. And I'll do all my calculations by treating that defect system just as a boundary condition. And there was one number that was taken from that SYK system. That was like the central charge of, I'm just mentioning SYK as an example, but, you know, some 0+1 dimensional system whose central charge was the only thing that was taken into the thing. But I was surprised by that, because there's an entire Hilbert space of that 0+1 dimensional system. What happened to that?
Well, okay. I wouldn't, okay, I'd have to go back to look at the paper if we want to, you know, parse out all the details. but I think they were really talking about a system like what I was describing. And you really want to have an exchange between the degrees of freedom in the bath and these defect degrees of freedom. I mean, I think they may have used boundary condition maybe in a liberal sense. It's not a it's not simply a boundary condition on the bulk or the bath degrees of freedom. I mean, you do need this exchange between the two systems to see the kinds of effects that we're seeing there. Does that help? Or maybe we should both go back and read the paper.
Yeah. Maybe I can ask you later offline.
Okay.
But there's one particular section where in the first paper, now you mentioned also a second paper, maybe I should go and look at that also. So in the first paper, there's one particular section where there is a calculation where indeed it appeared to me that the defect system was just replaced by a boundary condition. At least the formulas were of that kind. And as a result, it was a, yeah, I mean, it, well, maybe I should go back.
Let's take that offline, Gautam. I'm not going to be able to say anything more intelligent than I sorry.
Okay, thanks.
Any other questions? I don't think there are no more questions. So thank you very much, Rob, for giving this fantastic talk. So thank you everyone for joining, and I wish everyone a very nice time. So thanks again, Rob. Have a nice day.
Okay.
Yeah. Bye-bye.
Stay safe. Take care.
See you. Bye.
Thank you.
Bye.
Thanks a lot.
Bye-bye.
Bye.